Welcome to my physics experimental classes. Today's topic is rotational motion. This experiment consists of three objectives. The first objective is to determine the change in the angular velocity with respect to time and the angular acceleration of the system when the non-rotating ring is dropped onto a rotating disk. The second objective, which is very useful for us, that is to verify the law of conservation of angular momentum when the non-rotating ring is dropped onto a rotating disk. The third objective is to determine the percentage loss of rotational kinetic energy when the non-rotating ring is dropped onto a rotating disk. So here in all the three objectives, this last sentence is common. That is when the non-rotating ring is dropped onto a rotating disk. The apparatus of this experiment consists of the electronic balance, which is used to measure the mass of the disk and the mass of the ring, and a rotating platform which is very rigid, which consists of a smooth bearing, Pasco interface, disk, ring, pulley system, photo gate, and a laptop in which data studio software present. In this experiment, we come across many formulas. The first one, the moment of inertia of the disk, moment of inertia of the ring, total moment of inertia of disk and ring, angular acceleration, angular momentum, the percentage loss of rotational kinetic energy. All these formulas we will discuss one by one during our experiment. Let's take the primary measurements. The first one is the mass of the disk. So here it is showing that the mass of the disk is 1413.9 grams. So this is in gram. Obviously we need the SI unit, that is the kilogram. So simply divide with this number with the 1000, it becomes 1.4139 kilogram. So this is the mass of the disk. Okay, we are taking it as m1 and which is constant throughout this experiment. Now let's measure the radius of the disk. Okay, so we have measured the diameter of the disk with the digital vernier calipers. It is showing 228.64 millimeters. So this is the diameter. Obviously divide with this number with 2, so we get the radius in millimeters. Divide this number with 1000, so that we get the answer in meters. So that is the radius of the disk, capital R, equal to 0.11432 meters. This is constant in this experiment. So we have measured the mass of the disk, radius of the disk. So let's calculate the moment of inertia of the disk. The formula is half. So mass we have taken m1, so radius is capital R, so half m1 r square. So substitute the values, we get the answer 9.24 times 10 power minus 3. The SI units for moment of inertia is kilogram meter square. So this is also a constant value in this experiment. Throughout the experiment, moment of inertia for the disk alone is this much. Okay, next. Now our second object is the ring. Okay, so the mass of the ring, we have taken it as m2 and the mass is 1430 gram. So in the kilogram it is 1.430. Now let's measure the radius. Okay, for a ring we have inner and outer radius. So okay, this is the inner diameter. Okay, we measured with the help of the vernier calipers. It is showing 106.96 millimeters. So divide this number with 2, we get the radius. So this is the radius in millimeter. So divide with 1000 so that we can get the answer in SI units, that is in meters. So again this is a constant. So inner radius of the ring R, capital R suffix I, equal to 0.05348 meters. Now the outer diameter of the ring is 127.33 millimeter. Again we measured with the digital vernier calipers. So divide this number with 2 so that we can get the only the radius. So which is equal to 63.665 millimeter. Divide this number with 1000. So this is the answer. Okay, so now with the inner radius, outer radius and the mass, with all these three we can find the moment of inertia of this ring. So this is the formula to find the moment of inertia. We represent moment of inertia with the letter capital I. Okay, moment of inertia of the ring equal to half mass of the ring multiplied by square of the inner radius plus square of the outer radius. So substitute all the values, we get 4.94 times 10 power minus 3 kilogram meter square. Okay, so again this is constant throughout the experiment. Now let's calculate one more parameter, that is the moment of inertia of disk and ring together. So we have to simply add both of them. Just now we calculated individually the moment of inertia of the disk and moment of inertia of the ring. So simply add both of them. We get the answer 14.18 times 10 power minus 3 kilogram meter square. So we have taken all the preliminary measurements. Now let's get into the experiment. This experiment has a system consisting of two bodies. Say the disk is the first body and the ring is the second body. We have to study this experiment like before dropping the ring onto the disk, what is happening in the system, what are the parameters in this case, and after dropping the ring onto a disk, what is happening here, before and after studies. So it's like a inelastic collision. Okay, this is before collision, this is after the collision. Like this way we have to study, very easy. Let's start. Let's see the experimental setup. This is the pulley which is having a small holes. Mount the pulley onto the stand. This is the photo gate. Again mount this one also into the stand such that it straddles the holes in the pulley such that the pulley should rotate freely. Connect this photo gate to any one of the channel. Here we are using channel 1 to the Pasco interface. Now the disc having a D-shaped hole. Okay, the shaft also in the D shape such that our rotation will be perfect. Now this is about the ring, we know very well, keep it aside now. Now this is the Pasco interface. First connect this one to the power supply. So we have already connected to the photo gate. Now with this interface, today we are going to measure the angular velocity. Okay. Now connect this interface, the other end of the interface, to the laptop where we have the Data Studio software. So everything is ready. Now we are going to perform the experiment. We perform this experiment for 6 trials. Let's start the activity. The activity in the Data Studio program consists of angular velocity on the y-axis, time on the x-axis. The angular velocity is in radian per second and the time is in second. So both are starting from the origin O. So 0 1 2 3 4 5 on the x-axis, 0 1 2 3 4 5, like this one on the y-axis. So here we have many tools in this program. So out of many tools, we will be using this start, stop, fit to scale and the smart tool. These are enough. Okay, so here initially we rotate the disk, and after rotating the disk we start the program. So the system will record the angular velocity of this disk. Okay, ideally we should supposed to get a straight line like this, but due to the friction, okay, the angular velocity decreases, so slowly it will come like this. Now in this experiment we drop the ring onto the disk, so angular velocity suddenly decreases. Okay, and then it will come like this. So we can say this is before dropping the ring onto the disk, this is during, and this is after dropping the ring onto the disk. So like this we can say before collision, during collision, after collision, like this. So here this is the point of interest. So here we need the coordinates. So at this point, that is the initial coordinates, so initial time, and at that instant of time the angular velocity, and this is also another point of interest. So here also we should take the final instant of time and the angular velocity omega of the system finally. Let's start. We will be performing this experiment with 6 trials. Okay, the procedure is the same. Okay, just we will take different trials. So let's start trial 1. Rotate the disk and press the start button. Then we obtain a graph here and place the ring on it. Yes, this is the graph we are getting. So these are the point of interest. So take the smart tool and find the coordinates. Okay, so here, okay, so the coordinates, yes, make a note of this. These are the in trial 1, 4.6704, this is the time interval, 11.7 is the angular velocity. So now here this is the second reading. So next repeat the same thing for the trial 2, the same procedure, same thing, rotating this. Okay, so this is the angular velocity of the pure disk, dropping the ring onto the disk suddenly. Now this is the final. So like this, again here we have to note down. Okay, yes, this is the point of interest, Ti omega I, and here Tf omega f. This is in the case of trial 2. Okay, so the points are 6.5780 and here 7.1351. This is the time, and 8.6. Okay, let's go to the third trial. So I won't write anything, so observe carefully. Yeah, this is the third trial. Okay, so this is the initial angular velocity of the disk. Yeah, fit to the stop, then fit to the scale. Yes, okay, using the smart tool options, find the coordinates t comma omega. So this number 5.5945 comma 11.1. now another coordinate, the first coordinate, this is the x coordinate, that is the time, 6.1766 is the time, 7 at this time, instant of time, 7.1 is the angular velocity of the system, ring and disk together. This is the third trial. Same technique. So we will collect all the data up to 6 trials. The behavior is the same in the graph. Okay, so noting down these values. Okay, these are the readings in the trial 4. Let's go to the trial 5. Rotate the disk, start the program, drop the ring onto the disk, stop the program. After that, adjust if the scale is plot is not at the center, adjust it. Now to find the coordinates, take the smart tool. So here initially the coordinates are for time 6.0478 and 13.7 initial values. The final values are 6.6851 and 8.7. Let's go to the last trial. Same technique. Start, drop the ring onto the disk. Okay, stop it. Now bring it to the center, fit to the scale, smart tool to select the coordinates. Here at 6.038 seconds, 12 radian per second is the angular velocity of the disk. Okay, now at 6.5665 seconds, 7.7 is the angular velocity of the disk and ring together. Okay, the final means together. So we have taken all the 6 readings. Now tabulate the readings. So here the first objective is to determine the change in the angular velocity with respect to time. After that, from that change in the angular velocity with respect to time, we can find the angular acceleration of the system. Okay, so here we should note down that here there is no external torque is acting on the system. Okay, the disk is rotating. On the rotating disk we are placing the non-rotating ring, so it means there is no external torque is acting on the system. So in this case, okay, so there is a possibility for to get the angular acceleration. Though there is no net torque, we can get the acceleration here, angular acceleration here. Simply the reason is there is a change in the moment of inertia of the system. Okay, before the moment of inertia of the system is simply the disk. Now after, the moment of inertia of the system is because of the disk and ring together. So here the moment of inertia is changed, so there is a change in the angular velocity. Because of the change in the angular velocity, there is a angular acceleration. Okay, so let's tabulate the data, whatever data we obtained. Okay, so this is the first coordinates. Okay, ti omega I, this is before dropping the ring onto the disk. Okay, this is after dropping the ring over the disk. Okay, from these two coordinates we can calculate, okay, duration of the collision and the change in the angular velocity change. Okay, so the difference of these two is nothing but the change in the angular velocity. Okay, so we have the change in the angular velocity, we have the change in the time. So from these two, using the formula alpha, that is the angular acceleration, equal to d omega delta omega by delta t. So just divide 4.3, okay, with 0.6176. So the answer is 6.9624. So this is the angular acceleration of the system we got in trial 1. So like this, okay, for all others we have calculated the angular acceleration. So this is directly we got from the software, these two readings. Just what we have to do, we have to subtract the time with time and omega with omega, that's it, and then divide delta omega by delta t, we get the angular acceleration. Very simple calculation, okay, direct calculation. So we got for different trials, we got the different angular acceleration of the system. So these are the last two are kept vacant for you, so you please calculate this one if you understand this. Okay, so like this we have completed our objective 1 by determining the change in the angular velocity from that angular acceleration. Now let's go to the second objective, which is very interesting, that is to verify the law of conservation of angular momentum. Okay, so according to law of conservation of angular momentum, okay, the initial momentum of the system is equal to the final momentum of the system. So for this verification, for objective 2, we don't require any the time, okay, we need only the omega values. Okay, in the trial 1, omega I and the omega f values, only these two time intervals are not required. So whereas here we need the moment of inertia before dropping the ring over the disk, we need the moment of inertia of the disk, okay, which is constant for all these trials. Okay, so we got the moment of inertia, we have the angular velocity, multiply both of them, we get the angular momentum. Angular momentum we represent with letter capital L. Okay, capital L is given by moment of inertia I multiplied by the angular velocity. So like this, so multiply this with this, okay, we get this one. In the similar way, we have after the collision also. Okay, so here after the collision means the system consists of disk and ring together, so we have to take the moment of inertia of the disk and ring, okay, which we already calculated, and this part is constant for all the trials. Now, okay, we already noted down in the trial 1 we got the final angular velocity 7.4, multiply these two, okay, so we get the angular momentum of the system, okay, after the collision. Okay, so this is after value. So just have a look before and after values of the angular momentums. So here we got 0.10, okay, so here also 0.10, so almost they are close. So as they are close, okay, let's take the ratio of final, okay, the ratio final divided by initial, okay, so or we get, so I think in this case we have taken the final divided by the initial, okay, so we got the answer equal to 0.97, which is almost equal to 1. It means if the ratio is 1, it means that, okay, both are the, so here this value almost the same, okay, we can say angular momentum is conserved. So in the same way for the trial 2 also, okay, so we have taken initial angular momentum and final angular momentum, okay, initial moment of inertia of the system, that is the only the disk, we multiplied these two, we got this answer. The same thing, we multiplied this with this, we got this. Again we have to observe in the trial 2 also, let's observe what is happening here. Angular momentum initially, angular momentum finally of the system, okay, so 0.122, here also 0.122, so only in the fourth decimal there is a small difference. So we can say, okay, initial angular momentum equal to final angular momentum, so we can say that angular momentum is conserved. Okay, same thing for trial 3, 4, 5 for all of them. So again here in this case also 2 readings are left for you, okay, please calculate. Okay, So here too many calculations in this experiment. Okay, so we can say that the total initial angular momentum equals to total final angular momentum of the system. This will happen only when there is no external torque acting on it. Yes, we have performed this. Okay, there is no external torque is acting on the system. We have taken the disk, we have rotated the disk. Okay, so this is having the angular momentum. On this disk, non-rotating ring is placed. Okay, so this is non-rotating, so it means there is no external torque acting on it. Okay, so this is the statement. When no external torque acting on the system, the initial angular momentum is equal to the final angular momentum. That's what we observed in every case. So here this number, okay, almost the same. This number, same. Initial equal to final, okay. Like this we verify the law of conservation of angular momentum for a rotating system. Let's go to the third objective. In the third objective, we will determine the percentage of loss of kinetic energy. So this is one kind of inelastic collision. Okay, there will be loss of energy. We are dropping a ring onto a non-rotating ring onto a rotating disc. Okay, so it is a kind of inelastic collision. Obviously there will be loss of energy. So let's calculate how. Okay, the same thing, so let's divide this. This is before, this part is before the collision, and this part is after the collision. Okay, so before the collision we have moment of inertia of the disk. Okay, so which we already calculated in the beginning, so this is constant before, and the same, the omega I initial angular velocity of the system for every trial we have to put. Okay, and then kinetic energy formula. Okay, rotational kinetic energy, the formula is half, that is 0.5 multiplied by the moment of inertia of the disk multiplied by angular velocity, square of the angular velocity. Okay, with this formula. Okay, so 0.5 multiplied by this multiplied by this square of 11.7. so we get kinetic energy of the system, rotational kinetic energy of the system before dropping the disk onto the ring onto the disk is this much. Let's check after dropping the ring what happens to the kinetic energy, rotational kinetic energy of the system. So here it is very less. Yes, obviously we get a very less value, lot of energy loss we can expect because it is a inelastic collision. Okay, so here we observe, yeah, there is a difference, initially more kinetic energy, finally less kinetic energy. Okay, subtract these two numbers and divide with the original one, initial value, so multiply with 100, so we get the percentage difference. Okay, percentage loss of rotational kinetic energy, we got 38.60%. The same thing we observed that for trial 2 also, initially more kinetic energy, okay, afterwards less. Okay, so here also percentage of loss of kinetic energy, rotational kinetic energy is, okay, in this case also it is more than 35%. so like this we calculate for every trial. So whereas trial 5 and trial 6, these two readings are left to you. Okay, so I hope you understood this experiment, very lengthy experiment, too many calculations, but it is interesting. Okay, that's it. Thank you very much.